Example 20.8 is going to walk us through the importance of describing the variable that we are integrating with respect to. So if you recall, when we discussed derivatives, it would be beneficial to describe I'm differentiating a function f with respect to the x value. That's what that notation means. And when you integrate, you also tell yourself you are integrating with respect to which variable, dx. Here we're going to see integration in two different ways. That's really just going to provide two different methods of solving the same problem. We have the curve y is equal to the square root of x. And we have the function y is equal to x minus 2. And we want to find the area between them. So we can do so in two ways. First, we're going to integrate in the x direction. So we will take this function value minus this function value, and that will give us the length of that line. So we are going to take the top curve, the square root of x, minus the bottom curve. Well, the bottom of those red lines are the function 0. And we are going to integrate this from this point, which is the origin, 0, to this point. Let's figure out where that is. This function here is the line y is equal to x minus 2. It hits the x-axis when x is equal to 2, if y is 0. So we're going to integrate the x variable up to 2. That is going to take this red line and scan it and find us the area up to this point. And then we also have to add the integral from 2 to this point. Let me switch colors. This will be the blue lines. So let's find this point. This is the intersection of the square root of x function and the line x minus 2. And solving this, we get x squared is equal to x squared minus 4x plus 4. This becomes a quadratic. Oh, sorry, not x squared on that left-hand side, just x. So we have 0 is equal to x squared minus 5x plus 4, which factors as x minus 1, x minus 4. So these two curves are going to cross at 1, which is going to be somewhere right there. That's not where we're interested in. But they also cross when x is equal to 4. Now, the top of the red line is given to me by the square root function. But the bottom, oh, sorry, not the red line, the blue line. And the bottom of the blue line is given to me by the function y is equal to x minus 2. And that dx right there tells me I'm going to take this blue line and travel it from 2 to 4. So let's run through this. We have the integral from 0 to 2 of just the square root of x, plus the integral from 2 to 4. Oops, I don't know why I wrote an f over there. Of the square root of x minus x plus 2. Now, by finding antiderivatives of the square root of x, we get x to the 3/2 divided by a 3/2, or multiplied by 2/3. And we want to evaluate this antiderivative between 0 and 2. Oops, I'm actually taking the integral now. So we have the square root of x anti-differentiates to x to the 3/2 divided by 3/2 minus 1/2 x squared plus 2x, which we will evaluate between 2 and 4. A 2 being cubed returns an 8, so we have a square root of 8 being multiplied by 2 divided by 3. And then if we subtract this antiderivative at the lower bound of 0, we have just 0. We will add the value of this antiderivative at 4, which is going to be 4 square rooted is 2, 2 cubed, we have an 8. 2/3 times an 8 minus a 4 squared is 16 divided by 2 is an 8. Plus a 2 times a 4 is an 8. So let me wrap this in parentheses because we're going to take that value and subtract the value of this antiderivative at the lower bound. And the lower bound returns 2 to the 8th square rooted 2/3 square root 8 minus a 2 plus a 4. So when the smoke clears the room, your final answer is, let's see if we can simplify. I've got this 2 square root 8 divided by 3, and what ends up being a minus 2/3 8 squared. We've also got that minus 0, that doesn't matter. This minus 8, this plus 8, that doesn't matter. We end up with a 2/3 times an 8 from here, and then plus a 2 minus a 4. So that's 2/3 times an 8 minus 2, 16 over 3 minus 6 over 3. That's 10/3. Okay, we're going to do this exact same problem, but this time changing the order or the variable of our integration. We're going to do an integral with respect to y. Let me give myself a little bit more space, and let's sketch the functions again, adding all the relevant information. So now integrating in y becomes a good idea because you only have to draw one line. The upper bound is always given by this function. The lower bound is always given by this function. So to compute these, recognize that this line came from y is equal to x minus 2. So the x value here of this blue line, the upper bound, can be solved here. So x is equal to y plus 2. The lower bound is given to us by y is equal to the square root of x, which we can solve for the x value by squaring both sides. Y squared is equal to x. So the length of these blue lines is given to us by this value, y plus 2, minus this value, which is this x value, y squared. So we're going to integrate these blue lines with respect to y as y travels from 0 all the way to this y value. That's us integrating these blue lines. And the only question is, what is that unknown y value? It's either of these functions when x is equal to 4. So we can plug in y is equal to x minus 2. When x is equal to 4, we get a y value of 2. So that's the y value we integrate to. All right, now let's just do this. We have a minus y squared plus a y plus 2 integrating as y moves from 0 to 2. An antiderivative of this is minus 1/3 y cubed plus 1/2 y squared plus 2y. And we will find the area underneath this by taking this antiderivative at 2 and at 0 and finding the difference. So if we plug 2 into this antiderivative, we get an 8 divided by 3. We have a 4 being divided by a 2 and a 4. And we'll subtract the value of the antiderivative at 0, but there's y's in all terms, so it's just going to be 0. So we end up with a final answer of minus 8/3 plus 6. That's minus 8/3 plus 18 over 3. That's 10/3. And I think that's what we got up here too.